we also looked at the general calculations that are involved in the various types of collisions. In this lesson, we are going to look at some of the terms that will help us. So, we are going to look at the coefficient of restitution. We shall also look at the impact parameter. We are going to look at glancing collisions. We shall also look at impulse. We shall look at some of the explanations. We shall also look at calculations involving glancing collisions. So let's begin. You may be asked to define what is meant by coefficient of restitution. So by definition is the ratio of the relative velocity of separation to the relative velocity of approach along the line of impact. Moving at velocity u1, and this is u2. This is before impact. So if after impact these bodies move within velocities v1, v2, this is after impact. Now from the definition of our coefficient of restitution, which we are going to abbreviate as E, the ratio of the relative velocity of separation, so in this case E is equal to bracket. Now V2 must be greater than V1. So in that case we shall have V2 minus V1 divided by, now again U1 is greater than U2. So if this is my U2 for intercept result, so therefore we shall have U1 minus U2. So this is the ratio of the relative velocity of separation to the relative velocity of approach along the line of impact. Now for a perfectly elastic collision, E is equal to 1. For a perfectly elastic collision, E is equal to 1. For a perfectly non-elastic collision, E is equal to 0. So when you put E equals 0, so V2 will be equal to V1. For all other collisions, for other collisions, we shall get our E is greater or equal to 0 and less or equal to 1. So always that value. Actually E is just a measure of the elasticity for a given collision, and it is always between a 0 and a positive 1. So if you were given a perfectly elastic collision, you can also use this ratio. So example, and we've come up with this expression. By now, you may be forced to cram it. However, it is not always good to take everything as gospel truth. Sometimes you may be interested in also being part of those who can show it. And that's what we are going to do using this example here. We are having masses M1 and M2 moving along a straight line with the speeds U1 and U2. So after impact, so this is before impact. After impact, the masses move with velocities V1 and V2. Now, if the collision is perfectly elastic, prove that the coefficient of restitution is equal to 1. So this is what we are going to prove. So in any collision, you have to think of the momentum, and if it is perfectly elastic, you have also to think of conservation of kinetic energy. So solution in that case, so from linear conservation, we shall have our M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So you can call our first equation. Now, since the collision is perfectly elastic, we are also going to look at kinetic energy conservation. So from kinetic energy conservation, so we shall have a half M1 U1 squared plus a half M2 U2 squared is equal to a half M1 V1 squared plus a half M2 V2 squared. So this is our second equation. Now from equation 1, we shall have M1 bracket U1 minus V1 is equal to M2 bracket V2 minus U2. From equation 2, we shall have the halves will go. So we shall have M1 bracket U1 squared minus V1 squared is equal to M2 bracket V2 squared minus U2 squared. So now I'm going to divide these two, and also I'm going to expand this term in bracket using the knowledge that this is a difference of two squares. So this is now our refined equations. So dividing the two equations, we shall have 1 bracket U1 minus V1 divided by M1, so this is the same as U1 plus V1, U1 minus V1 is equal to M2 bracket V2 minus U2 divided by M2 V2 minus U2 V2 plus U2. So the M1 will go, the M2 will go, the U1 V1 will go, the V2 U2. So you remain with 1 over U1 plus V1 is equal to 1 over V2 plus U2. So now I'm going to rearrange this given expression there. This is the same as V2 plus U2 is equal to U1 plus V1. So if you compare what we are having with what you want to prove, so this is the same as V2 minus V1 is equal to U1 minus U2. And when you divide this on both sides, U1 minus U2, so you will eventually get 1 is equal to V2 minus V1 divided by U1 minus U2, which is actually the required expression. So for perfectly elastic collision, you can exploit this knowledge for the coefficient of restitution being a 1. Then with linear momentum conservation, you can solve any given challenge easily, even if you don't use the statement of kinetic energy conservation. So let's look at this new term, impact parameter. All along we've been looking at bodies moving along the same straight line, and we have also been sketching that after impact bodies continue moving in a straight line. However, there is a condition for that in order to be possible. So bodies can continue moving along the same line if originally the velocity vector of their center of mass are along the same line, and the distance of closest approach during impact being equal to 0. So in this case, the shortest distance between the velocity vectors of the center of masses during impact is what we call the impact parameter. So if the shortest distance is far much bigger than the dimensions of the colliding bodies, then those two bodies will never collide. If it is less, then a glancing collision will result, whereby after impact the bodies will move in different directions, i.e. they would fail to continue moving along the same straight line. So if you were asked to define what is meant by impact parameter, so impact parameter is the shortest distance between the velocity vectors, of the center of mass, of given bodies, during impact. So what you have to note, NB, so I'm going to use a B to denote or represent my impact parameter. So if B is equal to 0, a head-on collision results and the bodies would move along the same line after impact. So if B is not equal to 0 and it is less than the dimension of the bodies, so in this case if I'm to take the bodies to be spheres, so if B is less than the diameter of the spheres, then a glancing collision would result, and after impact the bodies would move or would not continue moving along the same straight line. So in that case, each would move at a certain angle from their line of impact. So I have used the match words. Now let me try to use a figure to represent my value of B. So if I'm having two bodies, so if this is the body 1, that direction, so for simplicity, let me assume I have another body which is body 2 at rest, and this being its center of mass. So the velocity vector of the center of mass is actually represented by the arrow which I have drawn there. Now if this body is to continue moving along the dotted line, since this line is not along the center of mass, then after impact, so this body will move in a direction as shown in the figure with a certain velocity, and then call V2, and again this one will also move with a certain velocity. Which I'm going to call V1. In this case, making an angle, maybe theta 1 from the horizontal, and also this one making an angle, which I may take to be theta 2. So in this case, now the impact parameter is going to be this shortest distance from this point to this. So in this case, this is our B, which is the impact parameter. So if two bodies were in motion, for example, if this was along this and it was moving whereby the velocity vector is along the center of mass, then after impact, again these bodies would continue moving along the line of impact. So impact parameter is important. So glancing collisions, so these result when the impact parameter is not equal to 0, and after impact bodies would move in different directions as shown in the figure. So glancing collisions, so these result when the impact parameter is not equal to 0, and less than the dimensions of the body. So bodies move in different directions, or in different direction after impact. So in this kind of collision, you might start asking yourself, can it be elastic, inelastic, or perfectly inelastic? So this kind of collision can be perfectly elastic or elastic if the kinetic energy is conserved. However, in most cases, we shall observe that kinetic energy may fail to be conserved. And since bodies don't stick together, then this kind of collision is going to be an inelastic collision. So we shall be splitting the motion of these two bodies into two. So we shall be looking at momentum conservation along the horizontal, and we shall also be looking at momentum conservation along the vertical. So mass m1 moving at speed u1. You can also have m2 at rest, that is before impact. Then after impact, you can have m1 moving with the velocity v1, making an angle from the horizontal which is theta 1. We can also have m2 moving with the velocity v2, making an angle. So from linear momentum conservation, so we are now going to break this into two components. We shall have momentum conservation along the horizontal. So along the horizontal, it will give us m1 u1 plus 0 is equal to, so you have to find the horizontal components of the velocity of the given velocity vector. So this one will be m1 v1 cos theta 1 plus m2 v2 cos theta 2. So that will be the first equation. Then along the vertical, so in this case, u1 has no component along the vertical. Therefore, the sum of the momentum before a collision is going to be 0. Now after collision, so we shall have m1 v1 sine theta 1 sine, then minus, because of this component moving in the negative direction, which will be m2, so this is v2 sine theta 2. So that is our second equation. Now if you are to solve for any unknown, then we must have at least 2 of the parameters not known and others are given. Remember, with only 2 simultaneous equations, you can only solve for 2 unknowns. So let's look at an example that may require you to apply that knowledge. we are going to use the knowledge of balancing collisions to solve for what is required. So a 500 kilogram car moving east with a speed of 25 meters per second collides at an intersection with a 2,500 kilogram van moving north at a speed of 20 meters per second as shown in the figure. Find the direction theta and the magnitude of the velocity v, that is the speed of the wreckage, after collision, assuming that the vehicles undergo perfectly inelastic collision. So the loss in kinetic energy. So we shall also have to calculate the loss in kinetic energy. So we are having our system of two bodies moving in the given. So this is of mass m1, this is of mass m2. This is moving at speed v2, and we are told that these two collide, and after collision they move with the velocity which we are calling v, making an angle theta from the horizontal. So this is going to be a composite m1 plus m2. So we can handle this challenge by splitting it into two. Then we shall conserve momentum along the vertical and the horizontal. So momentum along the horizontal. So from momentum conservation, along the horizontal, so we shall have m1 v1. Now this m2 has no momentum along the horizontal, so it's equal to m1 plus m2 v cos theta. Or we can have our m1 v1 is equal to m1 plus m2 v, and that is our first equation. So we are having two unknowns, v1 and theta. So you have to think of a second equation, and that is obtained by conserving momentum along the vertical. So momentum along the vertical, so momentum conservation along the vertical, momentum conservation along the vertical, so we shall have m2 v2, and this must be equal to m1 plus m2 v sin theta. So these are the two equations now that are important. So if we are to calculate the direction, I'm going to divide the two equations. Equation 2 divided by 1 shall have our m2 v2, m1 is equal to m1 plus m2 v sin theta divided by m1 plus m2 v cos theta. So when you divided equation 2 is to bring in this ratio of the tan theta. So when you simplify this, you will get your m2 v2 divided by m1 v1 equals tan, and when we substitute m2 2500 times v2, which is 20, divided by m1. m1 is 1500 times v1, which is 25. So we have simplifying, we shall get tan theta is equal to this will probably land 25 times 20 divided by 15 times 25. So this gives 4 out of 3. So theta equals tan inverse 4 divided by 3. Tan inverse. So this gives 53.13 degrees. In order to get the velocity, you substitute in any of the equations. So from equation 1, so the velocity v is equal to m1 v1 divided by m1 m2 cos theta. So you get your v equal to m1 when you add the 2, 4000 cos theta is 53.13. So v is equal to 15.62 meters per second. So that will be the answer to that speed. Now we are going to look at Roman grace laws. Kinetic energy, so we can call it KL. So KL equal to the sum of the kinetic energy before impact. So we shall have a half m1 v1 squared plus a half m2 v2 squared minus a half bracket m1 plus m2 v squared. So when we substitute, we shall get our KL is equal to a half m1 times 25 squared plus m2 v2 minus a half 16.625 squared. So the rest is now the work of calculator. when we try to simplify, 80,468.75 joules. So if the loss in kinetic energy was 0, then we would confirm that the collision was perfectly elastic. But since even these bodies moved interlocked, that alone shows that the collision is inelastic. Impulse is related to force and time, and it is defined as the product of force and its time of application. So with the knowledge of impulse, we shall be able to explain some of these general observations. For example, when catching a fast moving ball, you have to draw your hands backwards. Why? 2. New vehicles have inbuilt air-proof bags. What is the importance? Or how do those air-proof bags work? 3. A stone dropped from a certain height breaks a glass when it lands on it, and when a cushion is placed on the glass doesn't break when the stone is dropped from the same height. Another similar challenge is that when a body is being supported by a thread and the thread is jerked, the thread can break. So such questions, if you were asked to explain them, you have to look at the time at which a given force acts. The product of force and time of its application, and time of its application. So if I am to use my I to represent impulse, then it would be given by F times T, where time is where T is the time taken by the force when it is applying on the given body. However, from force being equal to mass times acceleration, which is the same as mass change in velocity, v2 minus v1 over t, we shall also see that impulse is equal to, so where there is a force, you can substitute this product m bracket v2 minus v1 divided by t times the time t. So this t will cancel, and we shall get our I equals m v2 minus m v1, in brief, which is a change in momentum, change in the momentum. So the relationship between impulse, we shall have our impulse is equal to Ft, which is equal to change in the momentum. So if I'm to use delta P, so this tool is important when it comes to calculating one of the given values. So it's moving along the y-axis with a velocity of 5 meters per second. After 5 seconds, it is moving along the x-axis with a velocity of 3 meters per second. Find the impulse delivered to the particle. Now, when you look at this example, from Newton's laws of motion, there is no way a body can change its direction or its velocity when no force is acting on it. So in this case, originally we have our particle moving along the y as given in the question. So our particle is of mass 3 kilograms, is moving with the velocity of 5 meters per second. Then after 5 seconds, it is moving along the x-axis with a velocity of 3 meters per second. Now find the impulse delivered to the particle. So from what so far we have seen, we know that impulse is equal to the change in momentum. So this is the tool that we are going to use in order to answer the given question. So depending on what has been given, it will dictate which of the two we are going to use. So given the mass is 5, the mass is 3 kilograms. Now this is in 2 dimensions. So we are going now to split the impulse. So we are going to find the impulse along the vertical, and also we are going to look at the impulse along the horizontal. So impulse along the vertical, if I call it IY, so will be equal to Fy and this will be equal to the change in the momentum. So the final momentum along the is 0 minus mv, where v in this case is the velocity along the y, which is 5 meters per second. So since time is given as 5 seconds, so we shall be able to get the value of Fy. So we shall get Fy is equal to negative mvy divided by t. So our mass is 3 times 5 divided by the time, which is 5, not forgetting the negative. So we shall get negative 3 newtons. So impulse along the horizontal, again using the same tool, Ix will be equal to Fxt, which is equal to a change in momentum along the horizontal. So we shall have 3, the mass mv x minus 0. Originally we had no momentum along the horizontal. So when you substitute, you will be able to get the force acting along the horizontal, which is given by m Vx divided by t. So the mass is what is given, 3. So the Vx is 3 divided by the time, which is 5. So this reduces to 9 divided by 5 newtons. So the resultant force is obtained from the components which we got. So resultant will be equal to the square root of fx squared plus fy squared. So f will equal to square root. Now the fx is 9 out of 5 plus the fy, which is negative 3 squared. And when we simplify, we shall be getting root. It gives us 3.499 newtons, and the impulse will be equal to the force times the time, which is 5. So we shall get 17.49 force time 20 seconds. So that would be the answer. Now going back to our first question, or on our first explanation, explain why when catching a fast moving ball you have to draw your hands backwards. So whenever you increase on the time the body is brought to rest, you are increasing on what we call the reaction time. So the force will significantly be reduced when you increase on the relaxation or the reaction time. The fast moving ball to rest, you have to draw your hands backwards in order to increase on the time taken to bring the ball at rest, so this has an effect. This has an effect of reducing the force, or of reducing the retarding force that will cause fracture. In that case, that would be the answer. So whenever you increase on the time taken for the body to come at rest, remember, for the body to decelerate or to retard from F is equal to MA is equal to MV minus U out of T. So our force is proportional to the retardation or to the acceleration. So when you increase on the time taken for the velocity to reduce to 0, then you are indirectly reducing that force. So if T is really very small, then the force will be quite big that would cause or that would result into a fracture. So by increasing the time taken for the velocity of the ball to reduce to 0, you are reducing on the magnitude of the force, the retarding force that is exerted onto the hands. Actually, it's the same explanation why vehicles have got airproof bags. So the airproof bags, or the airproof bag protrudes out in case a vehicle is involved in an accident. So it will prevent, or it will increase on the time taken by the driver to come into contact with the steering. So that increase in time greatly reduces on the force that is being applied on the chest, and therefore the occupant may survive in case of an accident. Again, it's the same story for a stone dropped. When you put a cushion, the cushion will increase on the time taken for that stone to come at rest the moment it strikes the glass or the cushion. So that increase in time reduces on the retarding force which is responsible for breaking the glass. Without the cushion, the moment the stone hits the glass, it will come to rest instantly. Hence, a big force will be exerted onto the glass, and which will cause, or it's the force that will cause the glass to break. So we are going to look at another example similar to what you have just covered a second. A 0.16 kilogram baseball is thrown with a speed of 40 meters per second, full stop. It is hit straight back at the pitcher with a speed of 55 meters per second. Roman 1. What is the impulse delivered to the baseball? Roman 2. Find the average force exerted by the bat on the ball if the ball is in contact with the bat for 2 times 10 to the power negative 3 seconds. Solution, we are given solution is 0.16 kilograms. So the speed, maybe I can call it U, is equal to 40 meters per second. Is hit back. So the final speed 55 meters per second. And again we are given the time t. 2 times 10 to the power negative 3 seconds. So Roman 1. What is the impulse delivered to the baseball? So from impulse is equal to the product of force, which is also equal to the change in the momentum. So in this case I'm going to use the change in the momentum. So if originally the ball was moving along with the speed u, and after reaching its direction, it changes and it moves with velocity 55, then the impulse, the change in the momentum, we are going to get the mass. So this is the final velocity minus the initial. So the impulse will equal to 0.16 times negative of v plus u. 40 plus 55 When you simplify that, you get negative 0.2 newtons. So the negative, it indicates a force in this direction, and therefore, so this is Newton second.